Welcome to Snark Chocolate, a show about ZK products, where we break them down with rich flavors and sweet insights. I'm Queenie, and I'll be co-hosting this episode together with Omer. Today, we're thrilled to be joined by Jonathan Passerat-Palmbach, Senior Research Scientist at Flashbots, for a deep dive into how privacy-enhancing technologies can address some of today's most complex challenges in blockchains. Jonathan, it's great to have you on the show.
It's a pleasure to be here. Thank you for the invite.
So first of all, could you please introduce yourself and Flashbots?
Sure. I'm Jonathan. I've been working in privacy enhancing tech for a while. I used to do a lot of applications on machine learning before, and I joined Flashbots a bit more than 2.5 years ago to keep working on privacy techs, but with the applications on the MEV landscape. And for those who don't know, Flashbots is like one of the pioneers and leaders in the MEV landscape, in particular focusing on like Ethereum and its broader ecosystem. So I guess we're going to talk in the podcast on like what MEV is and like what we're trying to do at Flashbots, because I think it's worth breaking it down.
Mm. Actually, I'm curious about Flashbots as an entity. It doesn't quite operate like a traditional company, NGO, or DAO. How would you describe what it is actually?
That's true. It's very peculiar. There's always been from the founders always wanted it to be an R&D collective primarily. Doesn't mean that we're only doing research. We're also building products, as you've noticed. But like, I think everyone in the company has like a very strong, at least R&D mindset, always trying to, harness like cutting edge technologies and like push the boundaries. That's why it would be labeled as like an R&D collective. And we're very proud as well of like what we call like the dual engine of product and research working hand in hand with like the product team at the forefront of what's going on in the MEV landscape and in the DeFi landscape, always like facing up new challenges and bring up super interesting questions to the research team, and the research team trying to address them and also like trying to bring new perspectives from a methodological standpoint. Sometimes it's like really a synergical collaboration in a sense.
That's very exciting, and I can feel how you're excited about the work as well. Yeah, so to begin, could you give us an overview of Flashbot's core products?
Right. So there's a few, and I think we can probably start with like trying to lay out what we're doing. I think the very crude summary of what we're doing these days is building blocks on Ethereum L1 and on L2 as well. And the inception of Flashbots was to try and address the MEV problem that had been proved to exist in a paper called Flashbots 2.0 by one of the founders of Flashbots, Phil Dyan and colleagues. And Flashbots evolved like a series of products to address MEV. In its first form, it was as a tool called MEV that was running back in the times of like proof of work Ethereum. And eventually that evolved into a software called MEV Boost, which was like a new version in a way of a software meant to be complementing Ethereum clients, but ready for proof of stake Ethereum. So that's probably like one of the software that most people know us for, MEV Boost. It's now run by like most validators on the Ethereum network, and it runs as a sidecar to your Ethereum client. So it's not a modification of the software. It's like an additional software that runs on top and collaborates with like the traditional deployment. So that's what validators see, let's say. Something that is more like on the end user side of the things. It's called Flashbots Protect. So it's just like an RPC that you might have seen that you can add to your MetaMask wallet, for example, to basically benefit from like all the MEV mitigation protection, better execution that the Flashbots product provide, but like without having to think or know anything about what's going on behind the scenes. So it's really like the entry point for anyone who wants to be part of like this ecosystem and not have like the negative downsides of MEV and still have very good execution. So that would be Flashbots Protect. And then you have a series of like tools that are used more by the sophisticated actors of the MEV ecosystem, like searchers and bug builders. And I think the flagship one that we released not so long ago is called BuilderNet. So it's like this decentralized network of block builders and still evolving, which is operated by Flashbots, by Nethermind, by many other operators and counting. So it's pretty cool because like that's ever since we've been doing things, we've released like open source software, but we were in a way like the primary custodians of this software. And now it's probably like one of the first like Flashbots product that is also like truly decentralized and run by different operators and not just Flashbots. So it's very good, positive feeling.
Cool. So it seems you guys are building or you're trying to improve the whole value chain of the block building.
Yeah. Yeah, I think that's a good summary. I think we're trying to improve the value chain of the block building, but with always the same kind of like guidelines in mind, with the idea that we want to provide faster, safer, cheaper execution for end users. To in a way like provide something that is a better UX than what you could have on TradFi. And I think at the end of the day, what is like at the heart of like Flashbot's product is to realize and to advocate the fact that MEV is not something you can really get away with, right? It
Mm.
will be there in one way or another, and we've shaped it like I don't know if it's like a an official thing. I've many people mention it from our team. I think it originated from either Bert or Phil from our team, but we have this concept of like the MEV trilemma, which says, as I said, like you can't get rid of MEV, so you just the only thing you can do is decide how it will be how it will be embodied in your system, right? So you can choose, for example, to not do anything. That was kind of like what was going on in the early days of Ethereum when MEV was discovered. And what was happening, you could see a competition between searchers trying to extract and access these MEV opportunities by outbidding each other in the public mempool. So they were basically spamming transactions over and over again to observe what the other bots were doing and trying to outbid them up until the block was finalized and it was the, in a way like finished. You couldn't outbid anymore. So the this first like shape of MEV is in a way spam. It's pure spam. You just like spam transactions, and by doing that, you create like a worse experience for everyone because you've got many transactions reverting. You need to increase the tips to win, so everyone has a worst experience at the end of the day. And that's something that you still see happening on chains where gas price is super cheap.
Mm.
So I think that's something we're going to see on other chains as well, maybe on Solana. These kind of things where if there's like very little money, very little like cost to get into the sending transactions, that's usually the form that MEV takes. Another one was very early, and that's what we see in some form of like even more modern mempools that we have is to say, okay, we will fix an ordering, and we will say, for example, transactions are sequenced in a first come first served scenario, right? That's something we hear very often that prevents MEV in a way. But what happened in that case is that you basically create a speed race, right? It becomes like a latency race to be as close as possible to the sequencer, to the block producer. And by doing that, ultimately, you centralize the network because everyone wants to be as close as possible to the block producer. So it's not great either, and it's also like not it's not great for open competition. It creates like a cost. You pay in a way the MEV by collocating, having like access to faster networking. It's kind of like what you see in HFT, but in high frequency trading. So we don't really want that either. And the final form is kind of like the one we adopted in a way, is to have explicit auctions, what we call like order flow auctions, where you acknowledge that there is value to be extracted from a transaction in a block, and in that case, you ask the searchers, so these more sophisticated actors, to name their price for having access to this opportunity. And if you do that correctly and like with a composition of like different tools, you can hopefully try to funnel this value back to the originators, to the end users. So that's kind of like what we're trying to do and the end goal, I would say.
Mm. Jonathan, I think it will be helpful if you can maybe briefly walk us through the block building value chain and tell us like the current MEV landscape in case, some listeners, some audience, they don't know the MEV space that well.
Mhm. No, of course. So I think maybe what some people don't really realize is that historically, um, we had like this public mempool on Ethereum where everyone was sending transactions, and that's how transactions were picked, formed into blocks, and there was like, in a way, historically the miners and then the block proposers in proof of stake Ethereum that were just like publicly trying to find these transactions. That's not really the case anymore. I don't have the stats at the top of my head, but like I'd say an overwhelming majority, if not 90% of transactions are not traveling through the public mempool anymore. For the reason that we've been discussing before, that if you just submit naively your transaction to the public mempool, it's going to be sniped by a bot, and you're not going to get the good execution that you want. You're always going to pay the worst price. So that's not great. So one way or another, these transactions travel through different pipes in a way to land into what effectively are private mempools with different forms of protections. And another thing that might not be very clear is that when we switched to proof of stake Ethereum, the goal, of course, was to now empower this cast of validators to be securing the network. So the last thing you want is for these validators to basically fall or be controlled by a single entity. Okay? Because if that happens, it means the network becomes extremely centralized and can suffer from censorship and all the downside of centralizations. And so the problem is that if you don't do anything in particular, MEV will de facto create like a centralization vector towards the validators. The reason is that if you don't particularly do anything and you let the validators extract all the MEV they want without doing anything, um, because you can set up validators by just staking more money, you can before you could create like just like more validators, and now you can just like stake more money in the same validator. The more stake you have in the network, the more MEV you're able to extract. And thus, the more money you have to re-inject into the network and become a bigger staker in the network, in a sense. So that kind of like was the landscape before we introduced this concept that the Ethereum Foundation pushed, called proposer builder separation. So it was part of the Ethereum roadmap, and it was the fact that if we acknowledge the fact that validators are in a way our top priority, we can maybe make a trade-off and say, okay, we want to keep these guys decentralized, but we are fine if like a specific type of actors, the block builders, can somehow become centralized, right? So that's the landscape in which we're evolving these days, where you have like a large set of validators on Ethereum that don't do much apart from like listening for blocks on MEV Boost. And you have like a very, very small amount of block builders that run very expensive and complex setups to produce these blocks that the validators then push on chain, basically. And I think up until recently, it was pretty much like just two large block builders building 90% of the blocks on Ethereum. So that's kind of like where BuilderNet fits in, right? It's the idea of like, okay, now that we've ensured that validators remain decentralized, let's try to address the next step. Let's try to make sure that block building also can somehow be decentralized by basically having everyone instead of like competing, collaborating into the block building infrastructure, so that we grow the pie for everyone.
Got it. So PBS actually was aiming to decentralize the block building process,
Correct. Yeah.
and then it resulted in some um, outcomes that may not meet the expectation, such as the centralization of the builders. So that's why Flashbots came in to solve the problem with BuilderNet and so as the other products.
So almost true. I think it was always known from the inception of PBS that that was a scenario, a very likely scenario that builders would be centralized. I think the only thing that Flashbots did is that instead of waiting for PBS to be enshrined in the protocol, we just proposed to build like this sidecar product that didn't have to be completely formally integrated in the protocol, just to trial PBS in practice. It turns out
Mm,
that what was it, like almost like 3 years after the merge, we still don't have enshrined PBS, and we're still running on the sidecar. But ultimately, the service is like served in almost the same way.
got it. Then, as a senior research scientist focusing on PETs, how does your work and expertise contribute to Flashbot's goal?
Right. So it's a very good question in the sense that it might not be obvious in the first sense where you need privacy in all these things. Uh, Same thing. Like I'm just gonna roll back like the history a little bit. If you look at like how all of these products were deployed in the first place, as I said, like they deployed at like as open source software, which is great, but someone needs to operate this infrastructure, right? Be it like block builders or even like the relays that are part of like this PBS network that we didn't really mention. And if you don't have any kind of like privacy technology in place, the only thing you can do is trust a third party, right? Trust someone. That's like the alternative to privacy in a way. And initially, that's what was happening, and that's still what's going on. When you interact with a relay, there's some kind of like social contract in a way that the relay behaves as you're expecting. But that's not great, right? We know from experience that we should aim for something that is not trusted. We aiming for like trustless networks in the kind of like systems we're trying to build. And so if you don't want to trust somebody with your transactions, with your blocks, with the executions you make on top of them, one way of doing that is to inject some kind of like cryptography, whatever flavor you choose. We can talk about that as well. But the goal is in a way to use privacy enhancing technologies to replace trusted middlemen. So decentralized flashbots in a way.
That's very cool. I think BuilderNet is a very good example that you integrated TEE into the solution. Could you tell us, the whole strategy here?
Yeah, yeah, yeah. So I think Bitternet is in a way like the result of like many experiments my colleagues have done before. We first like tried to run whole builders into SGX enclaves in the first place, even before TDX. And then we realized that there was a pretty good opportunity by adopting like TDX very very early on. And that's the benefits. The main benefit of it is that the overhead is very marginal compared to what you had before in previous like TE environments. So I think we are at like something around 5% overhead maybe compared to like something not running in an enclave. So which is very critical for this kind of workloads as well. Uh, and the idea with BuilderNet is to say, look, um, one of the important things that we want to have in as part of block building is that we want to offer uh, first pre-execution privacy, so pre-trade privacy to transactions, so that you can send your order flow to BuilderNet and know that no one is going to see it in plain text that used to be the case in the public mempool, for example. So that everything happens within these protected enclave environments. So it's like your confidentiality preserved in a way. And the second thing is that TEs also give you guarantees about the integrity of the computation. So you kind of like, if you trust how the TE functions, you can also trust that the output of any calculation performed in a TE has been done by a specific software. So if you verify the software that is supposed to run in an enclave before, and you verify when you start interacting with a TE that this is the exact same software you're expecting to be running, then you can have guarantees that what's happening to your sensitive data is what you expect. It's not being tampered with in a different form. And by doing that in a way, you can start to have things like, oh, now we can trust what the block builder is doing. So we can have guarantees on the way it orders transactions, for example. We know it's not like censoring transactions. We know it's not like trying to sandwich all transactions. We know exactly how the block building rules are being implemented by this block builder. So it's like a very strong guarantee in this direction. And and you also know by doing that that do you remember when I was saying that ultimately MEV should funnel back to the transaction originators? Well, in that case, uh, as part of BuilderNet, we can also implement what we call the refund rule, that basically refunds to the transaction originators either the extra gas they've been paying and they need to pay for the transactions to be included, and part of the MEV that their transaction have been generating. And if we didn't have any TE, the only way would be, oh, okay, just trust me, I'm going to refund you X, right? And you have no way to verify that this is true unless that's running in a smart contract. But then we go back to public execution and having to disclose the content of the transaction beforehand. So in the TE, what you can do is like get all of the benefits of the smart contracts, but at the same time apply this kind of like refund mechanics on transactions that are not public in a way. So users can have guarantees that yes, they're getting like a fair execution in a way, um, but without having to disclose publicly their transactions, if that makes sense.
Mm. So I can say BuilderNet is decentralized and trustless.
I think that's fair. I think we're gonna aim to have it like more and more decentralized. There's like currently there's a limited amount of like operators. I think it's like three, maybe four soon. And the reason why, and that's kind of like interesting because like we can maybe like dive into some more technical aspects of it. T's are not magic, right? It's no silver bullet. Otherwise, we would only be doing T's and no one would do cryptography, right? If they were perfect. Uh,
Mm.
so the thing is like one of the main limitations of the current generation of commercially available T's, let's say, um, is that primarily they do not defend against attackers having physical access to the T, right? So if I'm operating a T in my basement, for example, and I'm offering you the guarantees that I'm running a TE, you can trust that, but you have no clue what I'm doing behind the scenes on the machine, right? I might be inspecting it with like different forms of like more or less elaborate hardware to basically try to extract information from the TE. So as a result, what the main TE vendors did, Intel, AMD, all of these people would say, okay, let's reset like the playground here and say that TE is a cloud only technology. So that in a way, you don't trust the TE anymore. You trust a bit of the TE security, but you also trust the cloud operator not to be physically tampering with the TE that you're accessing. And as a result, what we do in BuilderNet is we say, look, if you want to operate a node within BuilderNet, it has to be a TE hosted in a public cloud. Okay.
Mm.
The thing is, we don't really know how to pinpoint a TE in a public cloud as of today. That's something that we're actively working on in the research team that hopefully will have some results on like very very soon. But otherwise, like even if today you say, oh, I'm renting this TE from Azure or from Google Cloud, for example, I have no way to verify that it's true, and that's an issue, right? Because like that's the only thing that we rely on for TEs to be trusted in this setting. So we need like a protocol to say, look, I'm operating a TE, and on top of that, I can show you that this TE runs from a cloud data center, for example.
Mm.
So that would be the next step of like decentralizing BuilderNet, uh, hopefully
Mm.
soon.
Yeah, what are the potential directions to further improve this TEE solution?
Right. So what I just mentioned is one. So for example, uh, having like being able to provide these guarantees that the T is like operating from um, from a cloud data center. That's critical, right? Until we can get to better TEs, and I think that's the in a way that's the end goal in the T arc in a way is to say, well, we have to jump through all of these hoops today because we're not very satisfied with the security that T's provide, right? We know that they have like this limitation if you have physical access, but we also know that historically, we had like side channels, we had many attacks that have been demonstrated against T's, more or less practical, right? Many of them are kind of like more academic exercises than real world attacks against T's, but we can't dismiss these attacks. And to make it short, one of the main reasons why these attacks are possible is because how these legacy TEs, like those available today, have been designed. They've been designed as a part of part of an architecture that is shared with the CPU. So you have like a component that is meant to be extremely secure, but that by design shares architectural elements with the untrusted CPU. In particular, I'm thinking of like cache lines, for example, but also the address and the memory buses that you have like on machines. And having like these shared elements of architecture at the lowest level of the hardware is inherently creating these design flows in T. So the goal, in a way, is to, and that's one of the things that we're actively doing at Flashbots, is to try and create better trust TEs that
Wow.
wouldn't have all these downsides in a way, and that would lift the limitations that we see in today's TEs.
Wow, that sounds like a huge task.
It's a big endeavor. It's going to take some time, right? Don't expect anything to come out of that, by end of year. But gradually, there'll be progress. There'll be communications. We're very openly communicating about what's going on in this line of research. And it doesn't mean that in the meantime nothing can be done, right? We don't have to just like wait until like these hypothetical better T's become available. We can
Mm.
try to do different things in the meantime. We can explore non-commercially available TEs, right? There's been a pretty big line of research in the academic space trying to uh, design different TE architectures. So that's one thing, that's readily available and that we can even try as of today. It's just a matter of bandwidth, almost in a way. We can also try to, TEs and cryptography don't have to be enemies, right? They can work hand in hand to enhance each other. So that's like a very interesting line of work as well to say, well, look, we don't want to trust only T's. We can kind of like try to build a defense in depth approach where the T's in a way is not anymore like the critical component of this architecture, and we can rely on software cryptography at the same time.
Mm. So that's trustless TEE.
First to see would be the end goal of what I was saying. It would be like building this in a way like much better. I don't want to say perfect, but like with like much better guarantees T's than what we have today. So no trust anymore in the vendor, reducing the trust in the supply chain of creating the T, um, and ideally not having to trust the location where TEs are operated from.
Would love to see that happen one day.
Would you say this is your main research focus at the moment? Maybe you can share more about other research projects, even past projects that Flashbots worked on.
Right. So the trusted CE's one line of work is one concrete focus that is led by my colleague Quintus, and it involves hopefully more than Flashbots. Flashbots is in a way uh, the customer in that case, and we're trying to, of course, help and think about it. But like there's many teams that have expressed interest and like are looking into helping us build these things because, of course, there's more applications than what we do. We also have on the research team people focusing just on mechanism design, for example. So, when I mentioned, for example, the refund rule that we're applying to refund users, it's not just an arbitrary thing. There's people trying to reason about what is the right way and right amount to refund to end users. They also think about, for example, many different things like what happens if you start to have cross domain or cross chain MEV, for example. What are the implications for the network? So that's the kind of like problems they're thinking about. And we also have like that's on my team we basically focus on like everything related to security and privacy. So we do a bit of like TE work as well, but we also try to do to harness like applied cryptography in a way to complement or enhance the TE applications that we have.
So it is like T is like your baseline in terms of hardware and security assumptions, and now you want to improve it in all sorts of different ways.
Correct. In a way, like TEs are the pragmatic choice because of like all the constraints that we have. I think the main two things that to characterize the workloads that we're trying to make more secure is that they rely on very complex legacy stacks of applications, right? Ultimately, if you think about BuilderNet, we're trying to run a full Ethereum block builder in an enclave. So imagine having to re-implement this whole thing in pure software cryptography. That would be very challenging, right? And the second aspect is that these things need to run at very fast speeds. And as I said before, like the current generation of commercially available TEs allow us to do that by incurring like very minimal overhead compared to like not running within a TE. Unfortunately, like today's cryptography is not quite ready to do that at that scale, right? It doesn't mean we cannot use it, but for such complex workloads, the overhead would be way too big compared to like what we are trying to achieve. So so
Can
the idea that we
you
have is, oh, sorry.
go ahead, go ahead.
No, I was about to say like the idea is to say, well, okay, if we can't really do everything that a block builder does right now, maybe we can find smaller pieces of the protocol to try and like implement with cryptography, for example.
I see. Can you be more concrete or give like some example on when trying to solve with like software-based cryptography um, meet get you to some kind of like a bottleneck, which makes it not very practical.
Yeah. So for example, we've been experimenting a lot with an MEV primitive in a way that we call backrunning. So backrunning in MEV is basically a searcher that spots could be an arbitrage opportunity to make it simple. So you've got a price discrepancy between markets, and basically you notice that a user transaction is triggering this price discrepancy. And because of how blockchains operate, you also know that even if the price is moving on centralized markets at the same time, there will not be any change of price between two transactions. So in a way, to have like certainties on the price on decentralized exchanges, the only spot where you have this kind of guarantees is right after the user's transaction that generated the price discrepancy. And so that's why searchers compete to basically have access to the slot in the block that is right after this user transaction. And that's called a backrun. And this is something that we've been playing with using software cryptography, using like secret sharing and more recently using FHE to try and show that a user could encrypt or protect, however you want to do it if it's secret shared, a transaction and make it available for a searcher bot for it to basically apply a searching strategy, so an MEV extraction strategy, an arbitrage or something like that on the encrypted transaction. But instead of doing that within a TE, you do that using what people call these days programmable cryptography. So all of the cryptographic methods like MPC and FHE that allow you to process data without having to decrypt them first. And so we have like a bunch of results on that, of prototypes and write-ups that have been presented at various places. The bottom line is that even that is still a bit too slow for what we want to do. Like to give you an idea, like the latest experiments I did with the FHE version of this protocol, for example. And I was lucky to have access to some hardware acceleration for FHE. So it's like kind of like really trying to push the technology as far as we can. We're still requiring about a minute to run on a very beefy machine. And that's something that I actually would run in like hundreds of milliseconds in real world constraints. So we're still a bit far from that, but we started from much further away. So all hope is not lost, and we're definitely not claiming that our solution is perfect. There's probably like still room for improvement in that. So maybe just maybe we can keep grinding a little bit further and try to get to like suitable runtimes for this kind of environment.
Maybe a bit intuitive jump, but I remember Flashbots also worked on Suave, hope I'm not butchering the name, which also deals with encryption. So maybe you can tell us more about like this product, where it is today, and how did you use encryption in Suave?
Right, that's a good one because we get that asked a lot, I guess. Like people are curious about Suave. Um, so I think Suave shouldn't be perceived as like a unique product. It's more of a vision that we want to push for basically realizing an encrypted mempool uh, using a decentralized block building scenario to basically address user intent. I think that would be the end goal, is to basically build the perfect user intent decentralized encrypted mempool that we can think about. And all of the products and experiments that we're either releasing as like production ready software or as experiments from the research team form in a way different flavors of Suave. So you can think that, for example, BuilderNet is like the decentralized block builder component of Suave. Uh, the encrypted background that I was mentioning before could be another piece of the jigsaw that comes into place and says, oh, look, now that we have a decentralized block builder, we can also offer a backrunning service on top of it, even though it's specialized. And I think what you will see in the coming month is that you'll have more and more of these like tiny pieces coming up, and all of that all together in a way form the Suave vision. So I think the confusion comes from like initially the first thing that were branded under Suave looked like, if I recall correctly, like some kind of like encrypted smart contracts using T's as like a coprocessor. So that's one way of like also providing different primitives, different like MEV-aware primitives to end users and to builders. It turns out that it was not probably like not the most promising direction to push for now. So this kind of like line of work has been paused a little bit in favor of decentralized block building, offering other products like for L2 and also bottom of block arbitrage that we've been pushing as well. So it's just like for now, it's mostly experimenting and trying to find what is the most suitable um, angle to advance like the decentralization of block building. So no pip
Yeah.
installs to have anytime soon. Sorry.
Jonathan, I'm also super interested in your work on federated learning and the collaborative AI. So, what sparked your passion for this field, and could you share some of your key findings with us?
Right. That's kind of like a fun story in a way. I was when I was like full time working in academia, I was working in a lab applying machine learning, deep learning to medical images, so very sensitive data. And we had like as part of a grant funding that we had to share this data with like the broader research community, which is great. Um, and I think intuitively I always thought that it would be a technical challenge, right? It's like very large data sets. You want to make them available to the worldwide research community. How do you do it, right? Do you put them on a cloud in a secure environment in a way? Do you broadcast them using BitTorrent or something like that for big data? But it turns out that it was more of a lawyer's issue on like how you draft the perfect data use terms that ticks all the boxes, that makes the hospital lawyers happy and allows patients to withdraw from the study with like completely crazy constraints. Like if someone withdraws from the study, we as like data curators have to make sure that all of the copies have been deleted in the world. So of course I cannot do that, right? I cannot go and like do anything more than sending an email to the people who downloaded the data. So I realized that that was not a practical way to operate on sensitive data. And at the same time, I met a community and their leader called Andrew Trucks, so the Open Mind community, that was pushing early on like the idea of like federated learning and privacy preserving ML. So I immediately realized that that was the thing we needed to do, and I completely refocused my research interest towards like federated learning and privacy preserving machine learning. So it's kind of like the insider story on how I ended up like working on these things. And I think if you want like kind of like the state of that as of today, it's mixed. I would say. I think the awareness of what these methods can do have definitely gained more and more attention, even like beyond the research community, which is great. At the same time, we don't really have any commercial traction for federated learning, for example, right? The main applications remain those that have been done by Google, I think, for training like the smart keyboards, which is great because like it addresses like many different users, but it's not the explosion of like decentralized machine learning that we were hoping to see, unfortunately. And I think there's many reasons for that. One is that it's not so trivial to convince people to join these decentralized AI networks. So we back into like kind of like the mechanism design landscape in a way. Like you need to find the right incentives to nudge users to come and like interact with these networks. And it's kind of like the same for privacy preserving ML. So I make the distinction between federated learning, even though sometimes it's like labeled as like a privacy preserving technique. I don't think it is. To me, it's more of a data governance technique where you have certainty in like where your data goes, but it doesn't give you any privacy as to what happens once the data is transformed and like in a way processed by the training algorithm. Uh, and for privacy preserving ML, in a way, there's two things. For input privacy, people are happy with like same thing like GDPR box ticking. So any kind of like service in the clouds, maybe like protected by a TE, will do in a way, right? You can just like go today in Azure, set up like a secure inference endpoint, deploy your model there, and you can give some security guarantees to users that their data is not seen by you as like the model owner. So it's not the demand for like cryptography driven PPML, privacy preserving machine learning, is not great because of that. On the other hand, I think the differential privacy community has seen like a bigger adoption because maybe like the impact of it is a bit more concrete. We've seen it being adopted even beyond machine learning for large scale statistics, for example, stats release in the US for the census data. We've seen it adopted by like big tech companies as well that want to provide some guarantees. Like Apple has always been like a strong force in this domain. So it's in terms of PPML, I'd say differential privacy is probably like the winner as of today in terms of like seeing adoption in a sense.
Cool. So I think I also talked to people who are working on AI, but sad truth is that privacy comes the second. So their their priority right now is still to to make the
Uh,
performance as better as possible. Yeah.
I think that's one thing. Performance is definitely one thing. But I think the blockchain and MEV landscape is a great example of what to do. I think ultimately, if you want privacy for the sake of privacy, you will always fall into these attractor of GDPR regulations box ticking, right? Because that's so easy to feel doing that. Why would you need like any advanced technology to do these things? Where privacy enhancing methods become really shine is where they unlock new use cases. And if you can do things that you couldn't do with the current playfield, that's where the demand for these methods is going to increase. And that's typically what we see in the blockchain and MEV space, right? Because like all of the things we're trying to do in MEV, providing like better execution, providing like verifiability, these are things we couldn't do, and especially in the decentralized world where there is no legal contract in place between actors, right? So it has to be either you trust or you don't. So this is the kind of like playing field where these methods really shine, and I think we haven't found that in the Web2/AI space because it's really about complying, uh, providing privacy by to comply with regulations. And to me, that's always going to be a very narrow scope of application for privacy and syntax. So we until we find use cases that just like demand privacy to work, I don't think we'll see like a large adoption as we've seen in the blockchain space.
And you would say the current mainstream or the most popular privacy enhancing technology for AI is still TE?
I think, yeah, in the sense that if you want to provide input privacy, so if you want to provide the input data you provide to a model, at least in terms of like obtaining predictions from a model. So, say you want to interact with ChatGPT or like whatever chatbot as of today. Right now, you're trusting OpenAI to not mess up with your data, right? You just tick a box somewhere that says, "Please don't use my data for training," but you have no way to know that they're doing it or not, right? You can't just know. So it's a very low hanging fruit to package these AI models in a TE to provide users with a guarantee that yeah, you're interacting with like a secure endpoint that runs within an enclave, and you can almost like audit the fact that the code deletes your data or at least doesn't send it somewhere else or tries to save it once the prediction was obtained. So that to me is like yeah a very low hanging fruit. And as far as I know, there are APIs doing that as a service in the major cloud providers. So yes, there's an overhead if you're running, and especially with AI models, they're pretty large. Even with today's modern TEs, you need to also harness like GPU TEs, which is probably like not as trivial as like harnessing like the regular GPUs that people are used to. But that's definitely something that would improve everyone's experience, I think, altogether.
Cool. Yeah, we hope PETs can make an AI powered world safer for everyone. Yeah, so Jonathan, before you go, we have one last question that we ask every guest. Please name a project you are bullish about.
That's a good question. I didn't think about that one. That's probably the one we'll have to retake. Let me think. I'm, I would say I don't know if I want to name one specific one, but I'm definitely bullish on like all the cryptography hardware acceleration projects. I mean, you guys being one, but I think we've seen that's something we've been discussing as well before. I think somehow we start to see a little bit of momentum in this direction, with like different teams announcing concrete results, right? Like things you can get your hands on, and that will completely change the expectations towards software cryptography. So yeah, I would say definitely bullish cryptography hardware acceleration teams. So go, please go.
Cool. Yeah, I guess that's all for today. Jonathan, thank you so much for joining us today. It was great to learn about the different aspects of Flashbots and your research work. For those interested to learn more, we've added some links in the show notes. Thank you, Jonathan.
Thanks so much for having me. It was a pleasure.
Thank you, Oma, for co hosting.
Thank you, Queenie.